Right, I think we can start. Hi, everyone. Welcome to the C3 AI DTI seminar series for the fall semester. My name is Gauri Joshi. I'm an associate professor at Carnegie Mellon University, and I'm co-organizing and co-hosting this semester seminar series with Professor Richard Xing, who is an assistant professor at the University of Illinois. Before we begin, we would like to pause to acknowledge the support of our academic and industry partners, for which we are deeply grateful. Our fall 2022 series is organized around two special themes, adversarial machine learning and distributed and federated learning. And our talks are scheduled to alternate between these two themes. We have some really exciting speakers lined up for the semester. So, of course, we'll be hearing from Professor Eric Xing today. And then from next week and in the following weeks, we'll have Professor Tom Goldstein, so Rachel Cummings and Pinyu Chen, who will be speaking in the seminar series. And our series will extend all the way until December. You can find the speaker information and abstracts on our website. And you can also find recordings of previous talks and future talks that will be available on the YouTube channel after every week's talk. So today we are very happy to welcome Professor Eric Xing to share his research through his talk entitled Machine Learning at All Levels, a Pathway to Autonomous AI. Professor Xing is a professor of computer science at Carnegie Mellon University. He's also the president of the Mohammed bin Zayed University of Artificial Intelligence and the founder and chairman of Petum Inc., which is a 2018 World Economic Forum technology pioneer company that builds standardized AI development platforms and operating systems for industrial AI applications. He completed his PhD from UC Berkeley, and his research interests span machine learning, statistical methodology, automated learning, and their applications to various artificial, biological, and social systems. So without further ado, let's welcome Professor Eric Xing. The talk will be 50 minutes long. And for the audience, you can use the Q&A feature to submit your questions, and we will ask them on your behalf at the end of the talk. So let me stop sharing, and Eric, you can go ahead and start whenever you're ready.
Well, thank you very much for the introduction. Let me get my screen ready. Let's see. All right. Can you all see the slides?
Yes, we can see it.
Great. Okay. Well, thank you very much, for the very kind introduction and also for inviting me. I just realized that I'm now kicking start the full semester whole series. It's a special honor for me to do so. So I'm going to talk about some of my recent work with my colleagues on machine learning at all levels. It's a big title. And also I kind of pivoted toward a hot topic these days, namely autonomous AI. Many people have been talking about that these days and offering various perspectives. And here I like to add some of my own perspective and opinions about how to achieve that and what's the pathway to approach this problem. So before I start, I want to acknowledge some of my key co-authors who contributed to this talk. I'm not going to read their names, but they are my former students and postdocs now working in various universities and companies. Now, I guess, we are now, at, the height of a machine learning, development and AI development, right? So we have seen a lot of progress in the past few years, in my opinion, often driven by, leaderboards and benchmarks, to push people developing more and more powerful models. And along this way, there now exists almost like an arm race, of computing power and resource to build larger and larger models for not only clearing the leaderboards on benchmark data set, but also to go for more ambitious goals, such as, very general purpose QA systems, big language models, and so forth. And these advancements leads to a lot of optimism in the field. And you see these kind of big claims that artificial general intelligence, AI consciousness being mentioned nowadays more and more often, by big players. But as academic, I guess many of us probably are aware that, we are still facing a lot of difficulties in even clearing some of the very fundamental problems in AI. For example, logical reasoning in complex fashion. The more logical steps that you want to reason about, the weaker you'll find these bigger models can deliver, probable answers. But here I want to actually even become even less ambitious and, maybe study, a more narrow and industrially kind of a relevant problem, such as building, AI systems for a real world application, say in healthcare, right? We know that in healthcare applications, there is, a wealth of data of all different modalities, and very rarely doctors' decisions are able to leverage on all these different, modalities of data, which are very complex and sometimes, highly corrupted and noisy. And how we build a system, right? Let's take a even simpler example, such as building a clinical report generator from a medical radiological image. And in building this model, in fact, this was a project in my team several years ago. We need to start by processing the data, extracting features, and then building various model components, and then, of course, launching them onto a system, serving them and tune them and so forth. This alone is already a major mission that could, keep the engineers and developers very busy, right? Now we ask, is any of this big model out there nowadays, or some of the future, trends of this big model able to answer this problem? I guess nowadays, much of the effort, in AI really has been focusing on building a smarter brain using larger and larger neural network architectures. And there has been proposals like this, a position toward delivering what they called a autonomous AI function that has components dealing with modeling the world, modeling the perception, modeling the actions, and so forth. But we don't actually see, any of these kind of efforts are directly delivering even a simple answer we need in real world applications. And I guess one of the issue, causing this gap is because the effort in academic research of deep learning are only focusing on this brain part, which obviously make our system very head heavy, but weaker on other aspects, right? We all know that in, say, a company like C3 or many other industry environment, in order to ship any, AI solutions, vertical solutions, we need to go through a long pipeline of, engineering and also research efforts, starting from data prep all the way down to, developments and deploying and serving cost optimizations and so forth. And this is like building a real creature that is autonomous, right? And you can see where our current effort mostly lands us is at the top, of our cognitive activity, which is having a very smart brain. But as we all know, even for every normal human being, we have a hierarchy of needs, starting all the way from physiological needs, food and sleep, and then safety needs, emotional needs, and then we talk about self-actualization and transcendence, right? And that's why I feel even for building the simplest machine learning and AI models, you need to look at not just the one level at the top, but also all levels beneath that through a proper descending, to the bottom. And that's basically coming to the focus of today's talk, how to recognize and formulate such a machine learning stack where, research or problems can be identified in a principled way to together deliver an autonomous AI system. I just want to remind us that most of the current academic efforts are maybe focusing on these two layers, which is modeling and learning. And there are some efforts focusing on like a data processing. And these other layers, such as incorporating more experiences of other kinds, meta learning, scalability, and infra management, are rarely the major focus of academic research. So today, I want to put all these layers of efforts together to take a holistic view to see where are the gaps. I think it is fair to state that at this point of view, at this point of time, there are, a lot of efforts already paid to different levels of a machine learning solution, but the quality and the level of sophistication and also the level of theoretical foundation is still inadequate, which causes uncertainty at all levels. So when we are talking about safety, trustworthiness, it's actually not just the trustworthiness, the robustness, and the quality of the model itself, like here. Even here, we have a problem of how to make composition of complex models, but there are other levels, such as how to tune big models, how to scalably train, how to federatedly train big models, how to schedule jobs, all become a problem. So the focus of today's talk is to select a few of these levels, to take a close look to understand how principled machine learning thinking and also solution can be also landed onto these other layers to form a more holistic solution of a machine learning as a system. So my plan is to touch upon these three levels, which is about learning, meta learning, and the scalable learning. And then we will see how to put them together to enable more composable and robust standardized learning systems. Okay, so to begin, how we learn, right? So we have many different paradigms and many papers published on various ways of learning. And why we need that many efforts? Because learning is a very complex task that needs to deal with a lot of different types of data in a lot of different types of environment, and also leveraging on many types of experiences. And here just a small collection of such examples, right? In addition to data examples, we want to utilize, for example, existing rules and constraints. We may want to interact with the environment to gain rewards and accordingly build our system, to act smartly. And we may also, have adversarial scenarios in our learning. And a combination of all that could make things more complex, right? And in addition to building models, to leverage on all these data and experiences, nowadays we have all these pre-trained big models. Are they getting us closer to solving, major solution problems? Well, maybe not, because the downstream tasks are so multi-purpose and diverse. There needs to be additional steps add on top of these pre-trained models, right? To, for example, fine-tune the parameters, to learn add-on components. And this alone, again, leads to the need of developing new methods, right? So all these different demands now leads to a big marketplace of algorithms and heuristics. I'm not even going to try name it, but you can see this is a very demanding kind of field requiring developers and the researchers to master a lot of informations, of each dealing with maybe a particular type of learning scenario. Right? So I think, to develop a more autonomous and the better learning system, one may want to start from systemizing machine learning to make a reduction and see how this marketplace can be a little bit more neat and standardized. Well, the same thing actually happened in other science before, right? For example, if you look at the physics, a few hundred, maybe actually 200 years ago, if you look at the field of electricity and magnetism, there are a lot more theories than we are learning now. The phenomenon of light, the phenomenon of magnetism, electricity, all have different laws named after Gauss, Faraday, Ampere, Ohm, and all that. But then the Maxwell equation, ventured to make a reduction of all this wide collection of different theories by unifying their notation systems and by also exploiting symmetries and the other type of regularities in their expression, to the point that they can be reduced to a mere 4 equations, which are known now as the Maxwell equation. And then based on that, people discovered new gaps in explaining certain phenomena, such as the constant speed of light and so forth. And then additional symmetry are brought into the theory to further reduce this set of equations. And all the way to, in this century, we have the Mills-Young standard model for physics that was able to unify, 3 of the 4 standard, natural force, namely electromagnetism, weak force, and strong force, all under the same set of equations. Right? So you may wonder, in machine learning or in AI, will we be seeing, such a standard formula that clean up our very diverse and noisy and busy world of algorithms and heuristics? Well, maybe there is a possibility. So for example, nowadays, we build different models for different tasks depending on different data. And how a standard equation may look like that at least cover what we've known so far in the field. So I suggest that this might be how such an equation may look like, right? So it contains a few terms. The first term can be called an experience term, which, as I show in a second, can be instantiated to capture all type of experiences, including data, rule, and rewards. The second term is defined as a divergence term, which defines a difference or a distance between 2 distributions. One is our target model that we want to learn, and the other is known as a variational distribution, which could be a placeholder as a stepping step to integrate new experiences with older version of the target model in an iterative fashion. And then the last term is an uncertain term, which functions as a self-regularizer to control the complexity model. So I'm not going to explain how this particular standard equation was formulated, but I'm going to reverse unwind this equation to plug in a few instantiations to show you how this formula can recover many of our known learning algorithms and formalisms. For example, if you instantiate the experience function as an indicator function over data instances and plug them back into the standard equation, you actually will be able to recover the loss function of the maximum likelihood learning parity. If instead you are assuming now data coming from an oracle and associate with the data a U function that measures the level of informativeness of the instance, and then instantiate the experience function as the sum of the oracle generator and also the informativeness of the instance, and plug them back into the equation, you actually recover an algorithm that is equivalent to what is known as the active learning algorithm. You can go on and replace the experience function with a expected future reward if you are in a interactive learning environment scenario with the environment, then plug them back into the standard model. You actually will recover an algorithm that is equivalent to what is known as the reverse RL algorithm. So I can go on and try various number of experiences and recover many of these instances. In addition to instantiating the experience function, you can also play with the divergence function. For example, in this case, we are going to replace the divergence function from what was before the cross entropy now into a Shannon-Jensen divergence, for example, and then furthermore plug a adversarial experience into the experience function. Then suddenly you are able to recover what is now known as the GAN, the generative adversarial network. And also, if you want to plug in additional fancier divergence function or experiences, you can actually also recover various different variations of the GAN model. So to sum up, by basically, instantiating a different experience function, you will find that all different type of experiences will play the same role, in utilizing this standard equation as the generic form of the loss function, and leads to different training dynamics. And if you want to further play with the hyperparameters of relative weighting between different terms, you can further control the information geometry and get more variety out of it. So that's basically, standard equation in a nutshell. It is basically a reduction or a summarization of many of the known learning algorithms that we are already using. So what's the big deal? So learning via a standard model, as I just shown, as a standard equation, actually gives you a lot of practical convenience in the first place. For example, one utility is to use the standard equation to perform something we call experience composition, which amounts to replace the experience function with a weighted summation of multiple experiences, each represent a particular type of information, such as data, such as rule, such as adversarial experiences and rewards and so forth, and create a holistic experience of panoramic learning. And I give you an example. For example, how to train, a controlled generator of text, right? And ideally, you want the text generator to produce meaningful contents, but also have a flexible control of sentiments and also are readable linguistically. But to train so requires a large amount of data. That means you need to have all possible pairs of contents and the sentiments and the language quality, which is often hard to achieve. Typically, what people have are some selected collection of, say, text under a certain sentiment. But even with that, you can already start, building, a controlled generator of text using a experience composition by integrating or by aggregating these three types of experiences. The first one is just the text and the sentiment pairs, of a small scale. And then the second one could be just a simple, sentiment classifiers based on, other type of training information. And then the third one could be, standard language models of trigrams and trigrams. And when you put all this together, you can learn, controlled generation of text that has a flexible way of switching between different sentiments while keeping the content still consistent, and also have a high quality of language and readability. And here we have a table showing you by adding experiences, one by one, you actually get more and more better and better score in terms of the quality of the production of the text. Another obvious utility of a learning experience using the standard model is what we call the transportation or the repurposing of well-known algorithms without reinventing the wheel. For example, we all heard about a very famous algorithm known as the policy gradient, right, which was widely used in reinforcement learning to learn reward functions and other things. But it is only used in reinforcement learning for that purposes. What about some other tasks? For example, in a different learning paradigm where we want to use rules from a knowledge base to regularize a learning. Typically, the rules are treated as given. But in many scenarios, we may want to start from a large set of unweighted rules and try to understand how different logical rules or constraints can be trade off from each other. That means that these rules needs to be parameterized, like what we did with reward functions in RL. And how to learn these parameterized rules? Well, actually, because the rules and also the rewards are just two types of experiences, which are seen to be no different, inside the standard equation. Therefore, whatever works for reverse RL can be also used for learning the rules in a pretty much same kind of algorithmic scenario, right? So here I have another example of building, virtual try-on systems, in small apps. Here you will see that not only you need to, learn from data, but also you need to utilize the rules of body pose to enhance the quality of learning, because the virtual try-on system is a very difficult system to train due to data scarcity. You don't have, individual, pose for all possible directions and gestures and wearing all possible kind of dress in your inventory. You only have a standard pose under a small number of dresses, but you can also utilize a lot of manually created body gesture rules to enhance the model in a kind of more kind of a data economical way, right? But on the other hand, these rules only are written for very stiff and pre-selected pose gestures, right? But when people are try on, they rotate freely. There may be interpolations needed between different preset rules. Therefore, you need to make these rule constraints soft and to be weighted. And that's exactly where the algorithm I just introduced can be used as a plug-in to learn a model with the knowledge-based constraints simultaneously weighted and learned. And here you can see an example of starting from the raw data based on a vanilla GAN model without any constraints and rules, into having fixed rules constraint incorporated into the model, and then learnable constraints incorporated into the model, which leads to better and better production of the images. So basically, the standard model can offer you a lot of flexibility, of creating richer experiences of learning and also borrowing different algorithms. In fact, you can almost imagine a master algorithm to be possible that runs on the standard model, which looks like this, right? This actually can be solved easily, by treating the standard model as a generic loss function, over, the space of auxiliary models and also the model parameters. And they iterate between two steps in the generalized. This actually looks very much like the EM algorithm, right? In the generalized E step, you update your Q model by integrating the experiences with the previous version of the model. And then in the M step, you update your target model by reducing the KL divergence or other divergence method between the teacher function and the student function. So this is also known, therefore, as a teacher-student algorithms. And there are many, many additional algorithmic tricks to allow smoothness, to allow kernel tricks and other a very advanced technology to be integrated into this generic placeholder of the algorithm. And now they can be easily applied to all sorts of learning scenarios. Right? And of course, simply having a standard equation as a loss function is not enough, right? You need to still, compose model architectures and also use the algorithm to train, this type of different architecture based on different models. But that actually isn't, posing particular additional difficulties, because in the prescription of the standard model, we didn't make strong assumptions of the P model and the Q model to be specifically constrained. In fact, all the different type of models can be plugged into this formula to get, supervisedly or, otherwise trained. Even the pre-trained model can be plugged in, into this framework if you want to build downstream submodels for add-on components, or want to fine-tune the subset of the model parameters in those pre-trained models, right? So again, it's about really incorporating additional experiences of all kinds into the subject to be updated, and then you can use the formula enabled by the standard equation to kickstart the training algorithm. So I felt the standard equation could be, a very neat vehicle, to push for more a number of applications, right? In here, for example, I summarized the following: learning with all experiences. We see that already. You can also explore complex interactions between experiences, using various mathematical tricks, such as the kernel trick that allows the quadratic interaction between different experiences. You can also perform theoretical analysis of the model and algorithm in a more standardized framework, so that the analysis result applies to different scenarios. And also you can use this formula to enable compositionality of bigger models from small building blocks. So let me pause here and see whether there are questions before I move on to another level of learning, also based on a principled optimization framework. Any questions at this point?
There are no questions on the chat yet. If anybody has questions, please feel free to type them in the chat.
Okay, thank you. Yeah. All right. So I just spoke about a standardized and more general kind of a framework for learning with all experiences. The next level that is crucial for building a holistic autonomous learning system, obviously, is about how to tune the learning system, right? This is also known as the meta learning, which worries about how to help the learning system to learn better, in the sense of hyperparameter optimization, neural active search, or even sometimes pipeline configurations. So this again, has been, how should I say, a slightly less clean and elegant, area in terms of the research approach. Many, of the existing efforts, are relying on, hand tuning, or, heuristics for defining the best configurations of hyperparameters, or, handcraft a neural architecture structure, and so forth. And obviously, there is a desire to automate this type of, problem. And but how to formulate this problem in a mathematically more principled way, right? Because unlike our machine learning problem I just described before, in here we are dealing with a system oftentimes not necessarily analytically expressible. For example, this entire job of training a model as a function of hyperparameter selection, is not necessarily a differentiable function that you can, take gradient and find the optimum point, or it is just simply too expensive to do that. And there are also, other training problems which is simply a black box to you. For example, you probably are not given the detailed structure of a pre-trained deep learning models and or large language models, and yet you still want to attune your prompts or your other kind of add-on models based on that. And then how do you actually mathematically assure that you are doing the optimum thing, right? So this problem is known as a black box optimization, which was actually studied widely in other scientific areas, such as material science, system of tuning, because when you do chemical reaction design, how do you decide the right proportion of compounds and so forth? Very often time is, a empirical experiments. It's a trial and error experiences. And the goal is to use the smallest amount of trials to achieve the best return and of the final configuration. And the mathematical formulation, is like following, right? You basically are in a search space of hyperparameters, or sometimes a neural architecture in the space and so forth. And your goal is to really design the optimum query, which is a very expensive, action, that's, entering the black box system, and the output, a outcome, which is, for example, your loss function, or maybe, how much electricity you use and the other qualification of the system. And obviously, the most straightforward thing to do is to start a grid search, right? And maybe also random search, and then until you get the best outcome. But obviously, in the high dimensional space, this is a very expensive thing. Doing every single experiment, could take you days, if not, hours, or even not days. So what I'm going to talk about now is a very generic approach known as a probabilistic Bayesian optimization, which gives you a principled and the general way of dealing with the problem of a black box optimization, optimizing, over, a black box function in terms of finding the best query to determine the best outcome. So here is the setup. The main idea is to use a probabilistic acquisition model to intelligently plan the query and perform efficient optimization. And what is this probabilistic acquisition model? It is basically a model that maps each configuration of the query X, for example, your choice of hyperparameters, to a uncertainty estimation over the objective Y. How certain you can kind of make over a configuration. And additionally, you also need to model the utility of the X, which is reflected in the very magnitude or the size of Y. And the determination of the next experiment X to do is usually a combination of the uncertainty reduction and also the utility maximization. And that's why it is really a doubly nested optimization problem. On the outer loop, you want to keep learning the probabilistic acquisition function to understand better the uncertainty. And in the inner loop, you want to also learn the acquisition function to better understand the utility of every experiment. And how to achieve that? Let me walk you through the algorithm. Here is how the algorithm looks like. Say you started from somewhere, you already have a few data points of X and Y pairs, and then you can fit a model on that. And we introduce a Gaussian process prior as a prior distribution of the function, the probabilistic acquisition model. And then our goal is to estimate a posterior distribution of such function. Okay, and we all know that a Gaussian process gives you a prior, gives you also a Gaussian process posterior. So it is very, very convenient mathematically to use this type of prior distribution. So that's basically how it looks like, right? This a gray sausage is the uncertainty over the probabilistic acquisition model. And these lines are basically samples of the probabilistic acquisition model under this posterior distribution. And then what you can do is to use it to compute the probabilistic acquisition function, which you can see is a reflectance of the uncertainty in different areas and also the value, the utility of that. Okay, you can actually go back and see that here you have a greater amount of uncertainty. Therefore, the alpha goes high. And here, even though the utility is high, but you are very certain about this particular point because you observe data. Therefore, overall, the acquisition function has a lower value. Using the acquisition function, now you can do an argmax and determine the next query to try. And then you get a Y, and that gives you a new pair of data points, and then you can update your function accordingly. So this approach hopefully can converge faster than a random or grid search, so that in the future you can just sample the X from this function to make sure that you have the best configuration for hyperparameters. So this approach is very generic because we make no assumption of the black box function form, and also very less dependent on the dimensionality of the parameters. And this panel of results shows you, that this approach, gives you, strong results over a wide range of models, such as random forest, such as gradient boost trees, such as a deep neural network, and also over a wide range of hyperparameter dimensions, ranging from a few dozen to more than 100. And in fact, nowadays, this topic has been really catching up industrial practice, and there are a lot more needs for this technology to meet new challenges. For example, there is a new topic known as, you need to use this for, neural architecture search, and in the Gaussian process, framework I just introduced, this can be very easy because in Gaussian process, you only need to know the pairwise distances between different, probabilistic trial samples. Therefore, if your sample is a graph architecture, you don't actually need to embed or make explicit the shape of the graph. You only need to measure the distance between two neural architectures using, for example, a optimal transport function. And then you just plug in such pairwise distance function into the probable model I just introduced, and to get the optimal procedure of learning the probabilistic models. And yeah, I just want to mention a opportunity that is now we are facing, how to actually move even further this effort of meta learning to make them amortized across new tasks. Because when we are using meta learning, not very often we are running into complete different new tasks. You are training every day maybe a new model that is by adding more layers and more depth and the width. But overall, the architecture may be very similar to the older models you use. Therefore, some of the older experiences that you used to train earlier meta learning models may be also useful for the current experiences. And amortized auto learning is really about saving those past trace of meta learning experiences into a database. And whenever running into a new training task, you make a regression over the history and then pick out the closest examples to the current one and start from there as an initiation point to hopefully save a few rounds of random trials. So this is what I want to say about the next layer, meta learning. And now I'm ready to jump into another layer that's touching upon systems. The reason I want to speak something about this is because this has been so far one of the areas least studied by machine learning researchers when they are developing their models, because they will often feel considered as an engineering detail that should be taken care of by the engineers in the company rather than by the researchers themselves. But I think there is opportunity here if we take over that opportunity. And here is a bigger context. So system machine learning now becomes a very, very important problems that needs to be solved. As we see, in this graph we saw earlier, in the past 3 years, the size of the machine model are growing in a very rapid pace, as well as the system hardware that is available there. And it is actually very difficult, for machine learning researchers to find, an easy way to deploy, their big models to a system in an easy fashion, even if the hardware is given. We have these generic tools, such as TensorFlow and PyTorch, that can be used to write parallel machine programs, but they are not very efficient, right? And then we have a very specialized system available in big companies, but they are usually made for specific models. What is really needed is something more generic that can be used to compile any old and new machine learning large models for any computational infrastructure. And that's where we see a need to define a new mathematical formalism, because the current practice are still very ad hoc. So back to where we were, we already talked about how to integrate data and experiences using the experience function inside the standard equation. And now when system and the models are taken into consideration together, you have to also introduce the model and the computer cluster into our objective, right? And then of course, how to map a model onto a cluster or a computer system is something called a strategy. That is exactly what we want to optimize. And then we can define a loss function over it. And the loss function could be the performance of the model, but could be also something else like the cost and the speed and so forth. And then the problem becomes a mathematical optimization problem. So here the challenge is that suddenly something new appeared in our loss function, which is the cluster infrastructure itself, which requires a proper representation. And likewise, the model needs a representation because this tool needs to be optimally aligned through a strategy, which also requires a formal representation. So our problem is to really, define a set of formalisms to turn a system optimization problem into a mathematical programming problem, and then using very standardized and simple approach to achieve optimal deployments of big models. Okay, I will give you a few examples. For example, in a recent, let me pass through this page. For example, imagine we want to build, deploy a large model, which are written as a single machine, a program into a cluster. What is needed is to really make proper choice of a number of system components, such as how communication should take place and how, communication consistency model should be selected, how to partition the model and the data, and how to pipeline the scheduling and so forth. And you want to really find the optimum path in this matrix of options so that you build a final strategy that can parallelize a serial program into a cluster, right? And that's the goal for solving this mathematical optimization problem. And I want to show you two examples that we did in the recent paper, for generally a generic solution for machine learning parallelization. So in one of this paper, we look into how parallelism can be mapped into computer cluster architecture. Because in large machine models, the way they are represented is through a computing graph of tensors. And in that representation, there are actually two types of parallelism. One is known as the intra parallelism, which amounts to dividing these tens of model parameters or data into subtensors. And when these are divided, large amount, make sure that mathematically we are still correct in computation. And then there's another type of parallelism which happens between different tensors across a computing graph. And when that happens, you only need to synchronize, the components occasionally to ensure mathematical correctness. Interestingly, in our current computing architecture, you'll see a similar dichotomy of the kind of the machine configuration. On the one hand, different computer boxes are connected through low bandwidth Ethernets. But within every computer box, you see multiple GPUs connected through high throughput, NV links. And if you have a program which allow the intra-op and the inter-op parallelism to be optimally mapped against this type of two-tier structures inside computer cluster, then you can achieve both mathematical correctness and also efficiency. And that's basically what our recent paper OPA is about. It started by analyzing the computing graph, slicing the big graph into pieces, and map them into a computer cluster mesh, and then look into each of the mesh structure and map the intra-op parallelism into cores inside a computer box. And this can be done by solving a dynamic programming problem for the inter-op path and an integer programming problem for the intra-op path. And the result actually is a very general purpose, almost like an AI compiler that can be used to automatically parallelize multiple machine learning models. And this graph shows you an example of the application. For example, we used APA to parallelize the training of GPT-3 and achieve a result that is comparable to the best human effort in partitioning this particular task. We were also able to achieve actually, a 8x improvement over a manual baseline when we parallelize the mixture of expert model, developed by Google. We were also able to achieve roughly a order of magnitude improvement of the speed when we were parallelizing a more complex network known as the wide rest network, which does not, enjoy so far a very performant, human configuration. Not only the throughput, can be improved over, a machine learning effort. Also, you want to make sure that the throughput is not compromising the statistical efficiency because, for machine learning people, unlike system people, they worry not only the amount of data being processed, in every iteration per unit time, they also want to make sure that the statistical efficiency in terms of the per iteration gain of a loss function is ensured. And that's not often the case if you want to just only push through system throughput. In fact, there is a sweet spot that is, giving you the best trade-off between the statistical efficiency and the system throughput. And again, we can use this, insight to define a new loss function, which is called the good put, that combines the throughput with statistical efficiency, and then let the system optimizer to optimize the deployments, of the computing task. And that program is known as a co-adaptive scheduling, which has been shown to have, a pretty generic performance over a wide range of tasks, over, human efforts. So in all, I want to just pinpoint, a few opportunities also in the SysML field. I think the new frontier right now is to really build a universal AI compiler, which allows, any model, to be able to deploy it on any scale, to, achieve, a wide range of goals in terms of the loss function, in terms of the performance measurements. And there are, again, a number of system and machine learning challenges that's way to be solved, which I'm going to pass over for the sake of time. So now, I guess, I'm closing to the end of the talk. So I talked about how to learn in a principled way, how to meta learn using a principled approach, and also how to, learn to compute optimally, in a distributed environment, also using a principled approach. But how to put them together? Because at the end of the day, our goal is to develop, a real world system, which, has, a pipeline of building blocks. And when we are talking about optimization, it is not about optimizing each components separately, but to really do them together in a holistic fashion. And when you're optimizing a pipeline, you actually run into competing objectives and also many tuning knobs along the way, right? So that really requires, an effort that allow the system to be highly modular and standardized, almost like, people play Lego, that they can be assembled and disassembled, hopefully using pre-made building blocks to avoid uncertainty and also, overly complex ad hoc implementations. And that basically is what I kind of see to be a necessary step to really move AI research beyond, the academic lab and make them more like a industrial production, like we do in, other industrial productions. And here are a few steps that I want to highlight, some of which are already enabled by what I just talked about in, the machine learning approaches at different levels. For example, we need standard nuts and bolts, such as the Lego pieces, to form the building blocks of such a system. And then we need to have a standardized architecture and the workflow to assemble them together through a proper pipeline, and also through more generic and interoperative formal representations. You'll see an example already when we are trying to align models against a system configuration, right? And then we also need to have a composability and certifiability strategies and processes, which allow a multi-level optimization to happen in a holistic fashion. Here, we need to really determine a proper mapping between solutions or configurations of a machine learning system at different levels. And just now, again, we'll see a few examples of how to map the model task, training task into a meta learning task, and how to map a big machine model into a computer clusters. And at the end of the day, what is desired is a outcome that is reusable and automatable and optimizable in a guaranteed fashion and in an analyzable and transparent fashion. And that's why I think a Lego and the standardized approach is more desirable. And here, I just want to flash at you how this Lego may look like. Right? Thanks to the standard model and standard equation, we were able to now at least decompose the model composition, of arbitrary type into, a set of predefined building blocks as listed in here. Even on the system machine learning aspect, many of the, choices of SysML aspects in computing, in memory measurements, in communication can also be predefined and pre-made. And here is just an example of the type of Legos that we use in building our output system and also the scheduling system I just mentioned. And there are lots of companies these that building ML op Legos, right? And here are just examples of this. With those in place, we can see, maybe a future kind of process of machine learning, to be really treated as Lego learning in the following way. You can use, a composer to build machine learning models from Legos. And here are examples of the tools, we built or from other third-party players. And then once you build models, you assemble model components into larger, composite models, or big systems using a pipeline composer, right? Here, again, we have multiple options of using something like Forte that we built in, my own team, or, many of the choices available, Kubeflow, Argo, like that, in other companies. But the gist of this pipeline is that they expose everything in the components, with a unified pipeline interface known as the public intermediate representation, so that you can furthermore undertake computational managements, auto tuning, and other deployment services in a unified fashion. Right? And that's where we can see an opportunity to really liberate developers from going to the details and try all the dirty work to put things together. Of course, underneath this system, you still need to worry about some of the core issues in different layers, such as standardized data representation, pipeline representation, and infrastructure representation, which allows such a mapping between elements at different layers through a principled and formal alignment and optimization exercise. So with that, I want to conclude the talk. I do think there is an opportunity to look into machine learning system development and the production at all levels, all using a principled and generalizable approach. And here are examples that we were able to achieve through our own research in my lab, and each of the a logo represents a particular effort into our solution at different layers. And that kind of leads me to think about how to redefine auto ML or autonomous ML, right? So in the good old days, and auto ML typically refers to automatically tune hyperparameters. But now with formal representations and standardized building blocks possibly available at all levels, you might be able to redefine auto ML through a multi-layer optimization crossing all levels, starting from data all the way down to infrastructure. And therefore, machine learning could be redefined as a much larger multi-layer optimization problem, which allows people to define performance over multiple aspects at system, user, and ecosystem eco level. And then the argument and the space of optimization can also go beyond just say model configuration, but all the way into experience configuration, pipeline configuration, system configuration, and so forth. So this is obviously a new paradigm for solving machine learning problem, which absolutely is challenging, but there are some initial efforts already out there allowing people to think about, at least experiment with multi-level optimization solutions for optimizing all these different objectives at the same time. For example, you can think about using multi-level optimization to jointly optimize the model, the meta learning, and also the system by a nested chain of a constraint optimization problem through either Bayesian optimization or differentiable approaches. And this is what I see to be a very interesting opportunity that could lead to the next generation of autonomous AI systems that we want to build in the future. So with that, I want to conclude my talk. Thank you for your attention. And if you are interested in playing with some of the solutions that I talked about, these are all available in an open source consortium called Castle, where we build a community of developers and researchers who are willing to share their codes and also contribute to the interoperability and the glue code between different components. So you are also welcome to contribute your own work into this system. Thank you very much.
Thank you very much for the talk. So if the audience has any questions, please type them in the Q&A box. If panelists have questions, they can unmute and ask the question directly.
I saw a question here already. How can you say more about how to make the Bayesian optimization more scalable? Yeah, very, very good question. That's indeed one of the challenge, right? It is already more scalable, at least, than a grid and a random search, but I don't know yet how to scale this approach to say tens of thousands of hyperparameters. So to be honest, I don't really know at this point a good answer to that. But I think there is always a trade-off of having very specialized. For example, if I know exactly what system that I'm going to optimize, I may be able to define a differentiable loss function so that I can bypass Bayesian optimization and using a gradient approach. The beauty of a Bayesian optimization approach is that it is assuming black box. It is more generic. So even though it is not as efficient as a first order approach, it is saving the time to solution effort by not necessarily requiring specialized implementations. So I think at this point, even if this approach is not totally scalable to very high dimension, it is kind of adequate for the system that we are building, for various healthcare and recommendation system that we're working on.
Eric, very nice talk. Shankar Shastri here. I wonder if I could ask you a question. You're part of a DARPA program where we're thinking about using, AI for complex designs. And then this last set of slides, when you were talking about nested optimization, have you thought about sort of multi-criteria optimization and sort of, how your framework might work? You had pictures of the aircraft and so on. And so the questions of how you think about Pareto optima and how would you deal with this sort of multi-criteria thing which show up? We've been asked to design with as part of this program, how to design an unmanned aerial vehicle. And it's been really challenging to understand how to put different criteria. And so do you have any thoughts on sort of?
Yeah. Very, very good question. In fact, that's exactly what I put in the last slides, as the new frontier, right? So this field of multi-level optimization is indeed, a platform or, a paradigm where you can plug in multiple objectives in a nested way, into different layers of optimization problem. And the trick, of course, is to make them connected in a hierarchical fashion that the optimization solution of the next layer isn't violating the previous one through some, hard constraints that tie together the two problems. So at this point, of course, we are using a very traditional constraint optimization approach to solve this in a kind of a nested fashion. So in principle, it's doable if this is efficient enough. But sometimes you want to even parallelize, different layers, and that's where I actually don't yet know, what might be the best approach to approach that.
Thank you. That's great. Thanks.
Thanks again to the speaker, Professor Eric Xing, and thanks to the audience for the questions. We'll see you next week for the next seminar.
Great. Thank you very much. Good to see you, Shankar.